All right. Let's get this party started. We're going to solve some problems here. And I'll just start off with what we have going on here. We're talking about free fall, talk a little bit of weight, a little bit of gravity, and here goes. An object is in free fall while a second object is falling toward the earth after having reached terminal velocity. Draw a force diagram for each and write a one-sentence explanation as to what they have in common and how they differ. So let's start this off. Let's talk about free fall. Let's talk about something that has reached terminal velocity. Now, hopefully, something in free fall is only being acted upon by force of gravity here. So it is accelerating downward. It is accelerating at negative 10 meters per second squared. So therefore, it is speeding up each second. It's speeding up 10 meters per second each second, right? And downward gives us the negative value. Whereas an object that is in terminal velocity has f of g down, you have f of air resistance upward, and these are balanced forces. However, the key to this is that here are my force diagrams where you have the air resistance is equal magnitude, opposite direction of f of g. So f of a air is up and f of g is down. These are equal in magnitude, only opposite in direction. So write a one-sentence explanation. So as to what they have in common. Well, they're both falling. They're both moving towards the earth, right? So they have negative velocities. But how they differ? Well, free fall, this object is accelerating, whereas in terminal velocity, acceleration is 0 meters per second squared. So how does mass and weight differ? Well, mass is kind of this fundamental property of matter, and therefore, when I say fundamental, it's like it's within the material, it's within the object, whatever you define. So let's just talk about a person, right? Your mass is going to be the same on Earth as it is anywhere, right? On the moon, on Mars, Jupiter, etc. So this mass is this kind of the total amount of stuff that kind of comprises you. But weight is force of gravity, and therefore your mass times the acceleration due to gravity, right? So here's your weight. Your weight is f of g. F of g is weight, and therefore it's simply how that mass kind of behaves within that gravitational field. So mass will be the same anywhere. Weight's going to differ based on acceleration due to gravity. So describe how two objects, one heavy and one light, will fall towards the earth in free fall, and which lands first. Well, hopefully by now you're saying, well, if they're both in free fall, I'll just draw something big and I'll draw something a little bit smaller. If these both drop from the same place, right, this one's gonna weigh more. This one's going to weigh less, but they're both going to fall at the same rate of negative 10 meters per second squared. They will both accelerate. Therefore, they will land at the same time. Right? Only gravity is acting upon them. Moving on. So what does net force acting on a mass have to do with acceleration? Well, where you find a net force, which I could write as anywhere there's a net force, means that the object must be accelerating. In other words, here we look at free fall. There's a net force downward. It's accelerating downward. If I were to draw a force diagram of an object on a table, right, call this f of g and normal force, and let's say I have a net force in this direction, applied force here, and I got a little bit of friction acting in the opposite direction. The net force is to the right. Therefore, it must be accelerating in the direction of the net force. So where there's a net force, the object must be accelerating. So a dog has a mass of 18 kilograms. What is its weight on the earth in newtons and in pounds? Okay, well, let's start this off. We know the mass. So f of g, weight is going to equal mass times gravity. 18 kilograms times 10 meters per second squared. The weight is going to be 180 newtons. Well, when I look at this here, when I continue to kind of solve this here, we're going to solve for pounds. So here's something that we've done in class. So I'm going to scooch this over for a second. You know, I'll scooch this up. So if I look over here, we've determined that 1 kilogram weighs 2.2 pounds. Pounds is a weight, kilogram mass. So I can set this equal to determining what the weight of the dog is in pounds. So I can set this up as a different proportion. 1 kilogram is 2.2 pounds equals, let's see, what was the weight? Oh, excuse me, 18 kilograms. There we go. Let's determine the mass of this particular dog equals X pounds. Here I can cross multiply 18 times 2.2 divided by 1. Gives me a total value of, 39.6 pounds. Scooch that over so you can see it. Come on now. 39.6 pounds. Cross multiply. So I set 1 kilogram over 2.2 pounds equals 18 kilograms over X pounds. So cross multiply, then divide by 1. So how much does a dog weigh on the moon, right? In newtons and in pounds. So let's do this. Let's do it. Do it. Okay. So I know that this dog here, so the dog here. So remember, its mass is going to be constant. So we've got 18 kilogram dog mass. In this case here, F of G is going to equal M times G. Mass is 18 kilograms times 1.6, negative, but 1.6 meters per second squared. And the weight of the dog in newtons here, I did not calculate this, so I had to grab my calculator here. 18 times 1.6, so it's 28.8 newtons on the moon. So if I want to solve for its weight in pounds, and there's a couple different ways you can do it, but I'll say this. I like this way. I know that on Earth, the dog weighs, let's see, what am I solving here? Oh, pounds. The dog in pounds. So the dog in pounds. I know that on Earth, it actually weighs 39.6 pounds on Earth, where G is 10 meters per second squared, right? And that's going to equal X pounds over negative 1.6 meters per second squared. Essentially, weight over G equals weight over G. And therefore, you would find that that dog, right, I cross multiply, right, so cross multiply and then divide, is going to be 6.3 pounds. Hopefully, that was beneficial, helped you out with free fall, weight, and gravity.